Very good afternoon to everyone in this course. I welcome you all for this battery technology for electric vehicle course. This part of the content is being presented in association with Professor S. Ramanathan. He is a faculty from the Department of Chemical Engineering at IIT Madras. So, he is talking about the technology part of it. I give an overview of materials that goes into the battery. The outline of the talk goes like this. So, the first we will discuss about what are the differences between the primary and secondary battery and how does voltage generate in a battery, because every battery has got a certain voltage. Not all battery gives same amount of voltage. That means there should be something related to the material that is used in the battery that define what is the voltage of the battery, right. And the internal resistance in the battery and its effect on thermal heating and capacity of the battery. Okay. So, the internal resistance of the battery is kind of leads to the heating while charging and discharging the battery. So, that causes sometimes thermal runaway issues, loss in capacity and so on. So, how to measure the voltage that is generated at the electrode electrolyte interface? So, that is another topic that we will discuss, and how to calculate the specific capacity of each of the active materials that we use in the battery, and how do we classify the materials as anode and cathode, because there are materials which are suitable for the anode. Generally they are low voltage materials, and there are materials which are suitable for cathode of lithium ion battery. They are high voltage materials. So, based on the voltage we will classify whether the given material is for anode or cathode, and we will do a comparison of the battery materials at some point in our lecture. And specifically I will discuss the structure of graphite, lithium cobalt oxide, which is called as LCO in the industry, and lithium titanium sulphide, and the energy storage mechanism, because lithium can be stored in the battery by several processes like intercalation, conversion and alloying. So, we will see in detail what are these processes mean and what is the advantage of using one over the other. And then the structural factors which limits the capacity in case of LCO, lithium cobalt oxide, and the choice of the electrolyte. So, not every non-aqueous electrolyte can be used for the lithium ion battery. There are certain qualities that electrolyte should have to act as an electrolyte in the battery. So, we will talk about that, how that electrolyte leads to something called solid electrolyte interface formation at the anode, and why is that important for the functioning of the lithium ion battery. All that we will discuss under this heading. Some more, then volume strain, because when you store lithium into anode or cathode, so when the lithium goes in, comes out of the electrode material, there will be a volume change associated with these materials. Yeah. So, that will lead to something called exfoliation in some kind of materials, or disintegration, or called pulverization of the electrode materials. So, this volume strain is a culprit that causes all these pulverization or exfoliation, such things which are not good for the battery, because they degrade the capacity of the battery and lead to thermal runaway issues in the battery. And we also discuss about the progressive formation of SEI. So, SEI in general forms during the first cycle formation cycle of the battery. If one made a good battery, like which can repeatedly intercalate, deintercalate the lithium without any other issue, probably the SEI will not grow with the time. Otherwise, there will be a growth of SEI with the time, which may lead to some unwanted chemical reaction, which can produce some gas evolution. That is why practically, you might have seen these batteries bulging as you use with age, right. So, these are all because of this SEI growth while cycling these batteries. Okay. So, I will discuss about that, and then I will also introduce few materials which are called strainless materials, and which will not cause any thermal runaway issues in the battery for long time. So, we will discuss some of those materials which are suitable for lithium ion battery, and I also do some volume calculations, volume expansion calculations using materials like graphite. And finally, we will talk about the strain at the cell level, and how do they overcome this strain at cell level in order to have very long cycle life for the battery. So, these are the roughly the outline of my talk. So, we will see one by one probably in the next 6 lectures, probably we will see all these content in detail. Fine. So, what is the primary battery and what is the secondary battery? Okay. So, primary battery we are very well versed with that. So, you may have this zinc carbon battery that we all use, alkaline battery like Duracell battery, where we have a zinc electrode in one side which is a negative electrode, and then we have a carbon electrode which is in touch with MnO2, manganese oxide. So, this is our positive electrode. Yeah. So, this we are familiar with, okay, and we also know this battery is useful, can be used only once. That means you buy this battery in a charged state from the shop, and then we load it in our appliances or portable gadgets. Then the battery start discharging the energy into the system. Once all the energy in the battery is utilized, it's pretty much waste. We can't recharge the battery, so we need to throw them. So that's called primary battery. This is a single use battery, and there is a chemical change which produces the chemical conversion, which produces the electrical energy. That electrical energy is what we use in primary battery. So, most of the reactions which are seen in the primary battery comes under the category of conversion reactions. Okay, conversion reaction. Why is called conversion reaction? For example, let us take zinc. So, in this primary battery, when you use zinc as anode or negative electrode, that gets oxidized to zinc 2 plus, okay, and goes into the electrolyte and produces simultaneously 2 electron, and this process is one way. That means in the given configuration we will not be able to recharge this battery, therefore we will not be able to bring zinc 2 plus back to zinc metal. So, this is not allowed. So, we have only zinc going to zinc 2 plus at the anode. Anode is also called as a negative electrode, and this act as an anode only during discharge. Okay. So, had it been a rechargeable battery while charging, then we will be doing the reduction of zinc 2 plus to zinc, then it is called as a cathode. Wherever the reduction happens, we call it as a cathode. Wherever oxidation happens, we call it as anode. So, oxidation means removal of electron. So, when zinc goes to zinc 2 plus producing 2 electron, it is called oxidation. Okay. So, let me show you this animation. So, in primary battery, so the energy available in the battery can be used only once, whereas in a secondary battery, as you could see, we can recharge the battery repeatedly. After every discharge, we can recharge the battery, right. I will rerun the animation for you. So, in primary battery, the energy that is available in the battery used only once, whereas in the secondary battery you can see we can have a external power source, we can charge the battery back to the full energy. And every battery comes with a capacity rating. You might have seen in the batteries numbers like 1200 milliampere hour per milliampere hour or 3000 milliampere hour, right. So, this denotes what is the capacity of the battery. Okay. So, what do you mean by the capacity basically? It is the total amount of charge that is stored in the battery, total amount of charge that is stored in the battery. Let us take an example and understand this. Let us take a lithium battery. So, lithium is the anode there. So, lithium will undergo oxidation, produces lithium plus and 1 electron. That means, if I take 1 lithium, 1 electron I would get. So, I can take 1 mole of lithium. So, 1 mole of lithium will produce 1 moles of electron, correct. And we know the charge on the electron is 1.6 into 10 power minus 19 coulomb, that is charge on 1 electron. So, what is 1 mole? 1 mole is the Avogadro number. What is Avogadro number? It is 6.023 into 10 power 23. That means, if I have 1 mole of lithium, it will have 6.023 into 10 power 23 atoms of lithium. Okay. How many? 1 mole of lithium metal would have 6.023 into 10 power 23 atoms of lithium. And we have seen in this particular reaction, 1 lithium produces 1 electron. So, let us multiply with Avogadro number, we will get the cumulative charge of 1 mole of lithium, okay, which is 96,485 coulombs. This also called as 1 Faraday, 1 Faraday, okay, which denoted with the symbol F. Okay. So, 96,485 coulomb is 1 Faraday. So, we can also express this in other units instead of coulomb or instead of Faraday, we can express in other unit which is ampere hour. How do we do that? So, we know 1 Faraday is so much coulombs. So, and 1 hour is correspond to 3600 seconds. So, you multiply by this factor 1 by 3600. So, you get 26.8 ampere hour. So, which is the capacity correspond to 1 mole of electron. Since 1 mole of electron comes from 1 mole of lithium, so this is also capacity correspond to 1 mole of lithium. What is 1 mole of lithium? Because we know from the periodic table, lithium has an atomic weight of 6.97 gram per mole. That means 1 mole of lithium is nothing but 6.97 gram of lithium. That means 6.97 gram of lithium could hold 26.8 ampere hour of charge. Okay, 26.8 ampere hour of charge. This is called capacity. Okay, this is called capacity. So, what is the capacity of lithium? So, lithium capacity, 1 mole of lithium correspond to 26.8 ampere hour. You can also express in the unit of ampere hour per gram, for which you need to divide. So, 26.8 ampere hour by 6.97 gram of lithium, then you would get in the unit of ampere hour per gram, right. So, now we have learnt what is a primary battery and what is a secondary battery. So, what is the capacity in the battery? The capacity in the battery is proportional to the amount of active materials that is present in the battery. In this case, I have taken lithium as active materials. So, if I have 1 mole of lithium or if I have 6.97 grams of lithium, which will be correspond to a capacity of 26.8 ampere hour, right. Now, how does the electrode electrolyte interface gains potential or gains voltage? Where does this voltage comes from? Okay, that is a question that probably we need to answer before going any further into this topic, for which we need to understand something called Fermi level equilibration. Fermi level equilibration. So, that I can explain you with an analogy. For example, I have a big tub here, it is a water tank, so with water filled up to this level, yeah, and next to that I have a narrow tank whose water level is lower than the bigger water tank. Consider this as metal and this as molecules. Okay. So, now what happens when you have these two tubs separately? There is no problem, you can store water to any different height. Okay. But if the moment you connect these two tank, the moment we connect these two tank with a channel, what happens? Because the pressure at the bottom is higher, okay, because this is proportional to the water head that is above that point, right. So, therefore, pressure is higher in this case compared to at this point here. Therefore, due to difference in pressure, the water will shift from this tank to this tank until the level on both the tanks are equal, okay, until the levels in both the tanks are equal. So, this is an analogy that I have given you. So, let us match this to metal. Let us look at the different metals here. Let us take lithium, which has a work function of 2.95 electron volt. What does the work function mean? So, every metal has got a conduction band and then it has got a Fermi level, okay, it is called Fermi level. Fermi level is the topmost point, the conduction point, the conduction band, which is occupied by the electron, okay. So, now if we have to remove one electron from this metal and put it in the vacuum, okay, if I have to remove an electron from the metal, put it into vacuum, we need to spend some energy because these electrons are bound by the forces of nucleus, okay. So, because of that we need to spend some energy to pull out this electron, put it in the vacuum, okay. So, that energy is called work function, that is a minimum energy that you have to spend. But that work function is not constant for all the metals, depending upon the metal you choose, the work function can vary. For example, alkali metals like lithium, sodium, these are all very electropositive. What I mean is they like to give the electron out, they like to get oxidized, right. So, these kind of materials will have a lower work function, okay. The materials like fluorine, okay, like chlorine, they will have, they are not metal, but they are elements like fluorine, chlorine, they are electrophilic, that means they like to accept the electron, they do not want to give the electron out, yeah. So, now let us consider two different metal, okay. Let us take in this case say lithium and say another metal is say zinc, okay. So, lithium whose Fermi level is higher compared to zinc, okay. That means to pull the electron from this level and put it in the vacuum, we need to spend less energy in comparison to zinc case. In zinc case, because this work function, that means this gap, okay, is higher compared to lithium case, we may have to spend more energy in order to pull the electron out of zinc to put it into the vacuum. That means this has smaller work function, lithium has smaller work function and zinc has larger work function. Now, if you bring these two metals in contact, you bring these two metals in contact, you would see the electron moves from a higher energy level to a lower energy level. Okay. In this case, the Fermi level of lithium is higher than the zinc. Therefore, when you bring these two metals in contact, you would see the electron moving from lithium to zinc. Okay. When this happens, you would see the positive charges are produced at the lithium side, because electron left lithium and landed in zinc, and the negative charges produced in the zinc side, because zinc received those electrons which came out of lithium. So, this charge separation cause a potential drop across this interface where these two metals are coming into contact. So, this is actually the origin of potential or the voltage development when you bring two dissimilar metals and join them. Okay. So, this in the case of metals is really depend on the work function of the metal, right. So, how do we extend this concept to our battery? So, in battery you have two electrodes which are dipped in the electrolyte. That means each electrode is in touch with electrolyte, right. So, you have a electrode electrolyte interface at the anode, again at the cathode you have an electrode electrolyte interface. So, there are two metal or two electrode electrolyte interfaces that are present in a battery. Okay. So, now let us look at very specific case. In this case I have taken a copper electrode. So, I have taken a copper electrode, I have dipped in a copper sulphate solution. The scenario is such, the Fermi level of the copper electrode is at higher energy compared to the lowest unoccupied molecular orbital of the electroactive species in the solution. What is the electroactive species in the solution? Because I have taken a copper metal and dipped in the copper sulphate aqueous solution, right. So, you have a copper ions moving around and you have sulphate ions moving around in the solution. Okay. So, now the copper, since it is at higher Fermi level, at higher energy compared to the LUMO, lowest unoccupied molecular orbital of the copper 2 plus in the solution, the electrons will leave from the electrode, land in the solution. Where will go in the solution? It will go to the copper 2 plus in the solution. Okay. So, the copper 2 plus will take the electron from the copper, it will reduce to copper 0, which is nothing but copper plating. So, the copper will plate on the electrode. Okay. So, copper 2 plus will be converted to copper 0, right. So, during this process the counter ion of this copper is sulphate. So, there will be an excess sulphate in the solution very near to the electrode, because the copper 2 plus is reduced to copper 0. So, the anion of it is in the solution now, okay. And since some electrons are taken away from the electrode will be positively charged. So, you kind of create a double layer. So, what is the double layer? The surface of the metal now is made of positively charged, and the surface of the interface where the electrode meets the solution, which is kind of negatively charged because of the sulphate ion. So, you have two layers, one positive layer in the metal and there is a negative layer just adjacent to the metal in the solution side. Okay. So, again you see an excess negative charge this side and there is an excess positive charge inside the metal. So, you will have a potential generated at the metal electrolyte interface. So, this is the origin of development of voltage, right. And let us take another case, say zinc metal dipped in zinc sulphate solution. The scenario is such, the Fermi level of zinc is lower than the energy level of your electrolyte. Then what will happen? Now, the zinc will oxidize, go into solution as zinc 2 plus. During that process, it will leave behind the electrons in the metal itself, because now electrons are added to the metal. So, the Fermi level of the metal would rise, because electrons coming out of zinc is left behind in the metal itself, and the zinc 2 plus goes into the solution. Okay. Now, the energy level of your solution will come down, because you are adding positive ions or cations to the solution and the electrons are added to the electrode. So, there will be a Fermi level equilibration here. That means, energy level both at the metal and the solution side will be same. Okay. At this point of time, your metal will have excess negative charge and the solution immediate to your electrode will have excess positive charge. In this case, it is zinc 2 plus. So, again there is a double layer created, and that would create a potential development in the system, right. So, this is how the voltage generates when you take a metal electrode, dip it in an electrolyte. Now, let us understand what is C rate in a battery. So, the C rate is how fast you charge or discharge a battery. Okay. C rate is nothing but how fast you charge or discharge a battery. So, let us take a battery. So, in this case this is my battery, yeah. So, the battery has a positive terminal and a negative terminal, yeah, and since when the electron flows, okay, okay, see the direction of the electron flow is opposite to the direction of current flow. This is a convention, okay. So, when I say I, that is a current. So, the current flow is opposite to electron flow. So, electron originates from the negative electrode during discharge and then it lands up in the positive electrode, yeah. So, this is what happens when you use this battery across a load. But this electron current in the external circuit is compensated by equal amount of ionic current inside the battery, okay. So, the ions are moving between the electrodes in order to complete the circuit. So, for the movement of ions there is a resistance in the electrolyte, therefore, there is an internal resistance in the battery. So, that I have shown here, okay. So, this is some few milliohms of internal resistance in the battery, okay. So, you might have seen on the battery the numbers printed like this, what is the capacity of the battery, right. For example, in this case 3000 milliampere hour, that means 3 ampere hour. 3 ampere hour worth of charge is stored in the battery, okay, right. So, the load can be anything. The load can be a simple resistor or it can be a microcontroller, okay, whose load will vary depending upon the intensity of the calculation this performs, right. So, now suppose let us take this case of 3000 milliampere hour, which is 3 ampere hour. This means the battery can supply 3 ampere of current continuously for 1 hour, then it will run out of energy. This is called 1C rate. That means the entire capacity in the battery is emptied in 1 hour. That is called 1C rate. Okay. Suppose I withdraw less current, because the load need not draw all the time same amount of current, depending upon the size of the resistor that you use in the load, or the intensity of the calculation that goes on the microcontroller, the load will vary with the time, right. Suppose I now draw only 1 ampere current instead of 3 ampere, the battery now will last for 3 hours. This is nothing but C by 3 rate. It means the entire capacity in the battery is emptied in 3 hours, that is 3C by 3. Suppose I draw 6 ampere current, then the battery will last only 0.5 hour, that is called 2C rate. So, as the current increases, C rate also will increase. So, if I empty the battery in 1 hour, that is 1C rate. If I empty the battery in half an hour, that is 2C rate. If I empty the battery in 3 hours, that is C by 3 rate. So, the C rate tells something about how fast we are emptying the energy in the battery, okay, right. So, how do you calculate how long the battery will last during discharge? Very simple. You take the capacity on the battery, in this case say 3000 milliampere hour, and you enter the value of load in terms of amps. Suppose I have a 3 ampere hour battery and I wanted to load say 0.5 ampere of current, it will tell you this will last for 6 hours. So, the battery life at the load of 0.5 ampere would be 6 hours in this case. Yeah. So, this plot here shows the performance of the battery at 2 different C rates. This is at 1 C rate, this is at 2 C rate. Okay. So, the C rate tells about how fast you are emptying the energy in the battery, right. So, the total amount of energy present in the battery is constant. So, that does not change. So, it means I should get the same amount of electrical energy out whether I do it at 1 C rate or 2 C rate. But if you look at it, the capacity I realized at 2 C rate is less than the 1 C rate, right, this much lesser at 2 C rate, right. So, at 1 C rate I had certain amount of capacity, but when I go to higher rate of discharge I have less capacity from the battery. Why is it? You remember the battery has got an internal resistance, okay. So, when you increase the current, so when you increase the rate at which you discharge the battery, then that resistant will also produce a energy loss, correct. So, I into R, right. So, that is the voltage loss that occurs across this resistor here. So, then you will have a energy loss or power loss across this resistor, right. So, that again proportional to the current that you draw. So, at 2 C you will be drawing more current than 1 C, therefore, the energy loss will be more across this internal resistor, therefore, the available capacity shrinks as you go to higher and higher C rate in the battery. Now, how do we measure the voltage of a battery? It is very simple. You take a voltmeter, you connect to the both positive and negative end, and then you can measure the capacity of the, you can measure the voltage of the battery, right. That means to measure the voltage of a cell or a battery, we need minimum 2 electrodes. 2 electrode electrolyte interfaces are needed in order to measure the voltage across a cell. Suppose I want to know what is the, because I told you earlier, when you take an electrode, dip it in an electrolyte, it will produce a voltage across the interface, right. In chemistry we call it as a galvanic potential, right. So, how do you measure what is the potential that is generated across electrode electrolyte interface of anode and cathode, of positive electrode and negative electrode? How do we know that? How do we find out? For that we can use another electrode which can act as a reference point, okay, which can act as a reference electrode. We call it as a standard hydrogen electrode. So, if you look at in the textbook, all the electrochemical reactions, okay, all the electrochemical reactions whose potential will be measured against a reference electrode, which is called standard hydrogen electrode, which will be listed in the textbook. So, any process you take, for example, fluorine plus electron gives you fluoride. So, potential of that is reported with respect to a reference electrode, which is standard hydrogen electrode. It is very simple. Standard hydrogen electrode has got a platinum coated with the platinum black. Platinum black is nothing but a high surface area of platinum, is a nanoparticle coated. platinum. So, that is dipped in a 1 normal hydrochloric acid. Okay. So, the concentration is 1 normal, okay. It is an aqueous hydrochloric acid, and into which we are hydrogen gas is bubbled at 1 atmosphere pressure. Into the solution, hydrogen gas is bubbled at 1 atmosphere pressure. So, this hydrogen gas gets absorbed on the platinum electrode, okay. It gets absorbed on the platinum electrode, okay. So, this interface, okay, this metal electrolyte interface whose potential is arbitrarily fixed as 0 volt, okay. So, that means we can take this as my reference electrode, we can take this as a reference electrode and couple it to any electrode electrolyte interface. In this case, for example, we can couple to one zinc. Let me get some space. So, let us dip it in a zinc. Let us take a zinc electrode, dip it in a zinc sulfate solution. Yeah. So, you connect them, we need to give a conducting path for the ion. So, we connect it with something called salt bridge. Okay. Now, we can measure this zinc sulfate interface. So, what is the potential generated across this interface, which this can be measured using a voltmeter by taking this reference electrode and connecting with a voltmeter. So, the voltmeter is connected across the reference electrode and the electrode of our choice, in this case zinc electrode dipped in the zinc sulfate solution, right. So, this is how you measure the potential. So, now let us take a reference electrode, in this case say standard hydrogen electrode, okay, SHE, and we can couple a voltmeter between this reference electrode and the positive electrode of the battery. That will tell you what is the potential generated at the positive electrode of this battery. And we can take the same reference electrode and measure the potential of negative electrode by this fashion, connecting a voltmeter. That will tell you what is the potential generated at the negative electrode, right. So, we will get the potential of the positive electrode as well as potential of the negative electrode with respect to a common reference electrode, which is standard hydrogen electrode, okay. So, now the difference in the value of these two potential is nothing but the cell voltage. Cell voltage is the difference in the value. So, this is a potential that is measured across positive electrode and this is a potential that is measured across the negative electrode. The difference of these two tells us what is the cell voltage of this battery, okay. This is how we can measure the individual electrode potential, okay, right. I stop here. So, let us continue in the next class.